BERT, Reading in Both Direction. Part 4, The Architecture, How BERT is Built. In Part 3, we saw BERT's core innovation, bidirectional encoding that lets every word see context from both directions. We saw the two training tasks, masked language modeling and next sentence prediction. We saw why this approach builds richer representations than left-to-right models. Now let's look under the hood. What is BERT actually built from? How big is it? And how does it take raw text and convert it into something the model can process? Think of Part 1 as understanding what makes BERT special. This part is understanding the machinery. Before we dive into architecture details, we need to understand BERT's overall framework, because it shapes everything else. BERT works in two distinct steps. Step 1. Pre-training. You take massive amounts of unlabeled text, billions of words from books and Wikipedia, and you train BERT on those two tasks we discussed in Part 3. Masked language modeling and next sentence prediction. Pre-training is expensive. In the paper's setup, it took multiple days on specialized hardware, but you only do it once per model. Step 2. Fine-tuning. You take that pre-trained model and adapt it to a specific task. Maybe sentiment classification, maybe question answering, maybe named entity recognition. For each task, you start with the same pre-trained BERT. You add a small, task-specific layer on top, then fine-tune the entire model end-to-end on labeled data for that task. Unlike the pre-training step, this step is cheap. It takes hours on a single GPU. Think of it like education. Pre-training is getting a comprehensive general education over many years. Learning language, grammar, reading, critical thinking. Fine-tuning is taking a short specialized course that builds on that foundation. Medical terminology, if you're going into healthcare. Legal writing, if you're going into law. Learn language understanding once, deeply, from unlabeled data. Then adapt it to whatever you need with small labeled data sets. This framework is why BERT became so impactful. You don't need Google-scale resources to use BERT. You just need the pre-trained model weights, freely available, and one GPU to fine-tune. Now, what makes this framework work across so many different tasks? The answer is the unified architecture. Here's something elegant about BERT's design. The architecture you use during pre-training is almost identical to the architecture you use during fine-tuning. What does that mean practically? It means BERT doesn't need different architectures for different tasks. Sentiment classification, question answering, textual entailment, named entity recognition, the same core model handles all of them. You're not redesigning the architecture for each problem. Before BERT, researchers often built custom architectures for each task category. Comparing two sentences? Design a model with separate encoders plus a comparison mechanism. Classifying a single sentence? Design something different. BERT uses the same multi-layer bidirectional transformer encoder for everything. The only thing that changes is the small output layer you add on top. Think of it like a Swiss Army knife. The core tool stays the same, but you attach different small adapters for different jobs. This is one reason BERT spread so quickly. Once you understood BERT, you could apply it to virtually any language task without architectural engineering. Now let's see what this architecture actually consists of. BERT's architecture is a multi-layer bidirectional transformer encoder. If you've listened to the Attention series, this should sound familiar. BERT takes the encoder stack from the original transformer paper, those layers of self-attention and feed-forward networks, and uses them directly. Same scaled dot product attention mechanism. Same multi-head attention splitting representations into parallel heads. Same position-wise feed-forward networks. Same residual connections and layer normalization. So, if you already understand the transformer encoder from the attention series, you already understand most of BERT's architecture. The key difference, which we covered in Part 3, is that BERT uses full bidirectional self-attention everywhere, whilst models like GPT use masked self-attention that can only look left. That architectural choice enables everything else. Now let's get specific about model sizes. The BERT paper introduces two main model sizes. Think of them like two engine sizes for the same car design. The paper uses shorthand notation that looks intimidating at first, so let me explain it. L is the number of layers. How many transformer blocks are stacked vertically? H is the hidden size, the dimensionality of the vectors flowing through the network. A is the number of attention heads. How many parallel attention computations happen in each layer? Now, here are the two configurations. BERT Base has 12 layers with hidden dimensions of 768 and uses 12 attention heads. In total, that gives you 110 million parameters. BERT Large doubles down. It has 24 layers, increases the hidden dimensions to 1024, and uses 16 attention heads. That brings you to 340 million parameters. The result? BERT Large has roughly 3 times as many parameters. Imagine building understanding of a sentence by passing it through a series of refinement steps. BERT Base takes 12 steps, with each step working in a 768-dimensional space and using 12 different perspectives through multi-head attention. BERT Large takes 24 steps, double the depth, with each step working in a larger 1024-dimensional space and using 16 perspectives. More layers means more opportunities to refine understanding. Larger dimensions mean more capacity to represent complex patterns. More attention heads mean more ways to look at relationships between words. Generally, more parameters means better performance, but also more memory and compute requirements. BERT Large performs better on benchmarks, but requires more resources. Now here's an interesting detail about why BERT Base has these specific numbers. OpenAI's GPT, which came out just before BERT, also used a 12-layer transformer with 768-dimensional representations. Also, roughly 110 million parameters. The BERT authors deliberately matched GPT's model size. Why? To make the comparison scientifically fair. If BERT had been much larger than GPT, say 300 million parameters versus 110 million, and BERT performed better, skeptics could argue, of course it's better, it's just bigger. You threw more parameters at the problem. By matching the model size exactly, the BERT authors isolated the key variable, the architectural choice. BERT Base and GPT have the same number of layers, the same hidden dimension, the same parameter count. The only difference is bidirectionality. By matching GPT's size, they made the comparison fair. The key architectural difference is attention direction. BERT is bidirectional, GPT is left to right, though the paper also notes a few training recipe differences in the appendix. So when BERT Base outperforms GPT on understanding tasks, you can attribute that to the bidirectional architecture, not to model size. That's why BERT Base has those specific numbers. It's a controlled experiment showing that bidirectional attention matters. BERT Large is simply, let's see what happens if we scale this up. And it does. BERT Large achieves even better results than BERT Base. Now let's look at how BERT handles input. Before BERT can process text, it needs to convert words into numbers. And here's where things get elegant. BERT doesn't use just one type of embedding. It uses 3 different embeddings and adds them together. Let me walk you through each one. First, token embeddings. Every word, or more precisely, every word piece, gets converted into a vector. These are learned during training. Words that behave similarly end up with similar embeddings. For example, cat and dog might have similar vectors because they're both animals. However, and but might be close because they play similar roles in sentences. Second, segment embeddings. Remember, BERT can process sentence pairs. But how does it know which tokens belong to sentence A and which belong to sentence B? That's what segment embeddings do. Every token in sentence A gets one embedding to mark it as belonging to the first sentence. Every token in sentence B gets a different embedding to mark it as belonging to the second sentence. So the model always knows which sentence each word came from. Third, position embeddings. Just like the original transformer, BERT needs to know word order. The first position gets one embedding, the second position gets another, and so on through the sequence. BERT learns these positional embeddings from scratch during training, rather than using the fixed sinusoidal positions from the original transformer. Now, here's the key step. For each token, BERT takes all 3 embeddings and adds them together. Token embedding plus segment embedding plus position embedding equals input representation. So if you're processing the word cat at position 2 in sentence A, the input representation combines 3 things: the token embedding that represents the word cat, the segment embedding that marks it as part of sentence A, and the position embedding that places it at position 2. 3 pieces of information: what, which, where, combined into one vector. These 3 embeddings, token, segment, and position, combine to give BERT everything it needs to process each word in context. Now let me show you one more crucial piece of how BERT handles input: the CLS token's special role. You'll remember from Part 3 that BERT adds a special CLS token at the very start of every input. Understanding why this token matters is crucial for how BERT works. The CLS token always appears at the very start. After processing through all 12 layers with bidirectional self-attention, this token has attended to every other token in the sequence. Think about what that means. Dog attended to cute and likes. Cute attended to dog and playing. And CLS attended to everything. It built up an aggregate representation capturing the meaning of the entire input. When you need one vector that summarizes everything, like when classifying sentiment or predicting whether sentence B follows sentence A, you use the CLS token's final representation. It's BERT's way of providing a clean interface for sequence-level tasks. You don't need to design custom pooling strategies. Just take CLS and use it. Putting everything together. BERT works in 2 steps: expensive pre-training once on unlabeled data, then cheap fine-tuning many times on task-specific labeled data. BERT uses a unified architecture, the transformer encoder with bidirectional self-attention, for both pre-training and fine-tuning across all tasks. The architecture comes in 2 sizes. BERT Base has 12 layers and 110 million parameters. BERT Large scales up to 24 layers and 340 million parameters. BERT Base was specifically sized to match GPT for controlled comparison, proving bidirectional attention matters independent of model size. Input representation combines 3 embeddings: token, segment, and position. The CLS token provides an aggregate representation after attending to everything. That's how BERT is built. The framework, the architecture, the model sizes, and the input representation. Coming up in Part 5, we'll dive into the pre-training mechanics. How exactly does the masked language modeling work? What is the 80-10-10 strategy? How does next sentence prediction actually train? And what does BERT learn from? Why books and Wikipedia specifically? We'll see the training details that make BERT work. But for now, you understand the architecture. You know the building blocks and how input flows through the system. The machinery is clear. Next, we'll see how it learns.